So welcome to the pre-recording of lecture 7, our fourth session in the summer on an introduction to symbolic computation. So in this part, I hope to explain the main concepts and the main topics for this lecture. So we will look into the number types and mainly how the number types are represented, in particular what are the implications for the binary number system. And then in the second part I hope to explain how functions may be used to store data. Um, so the topics in this lecture appear rather technical, but they do have consequences later on. Okay, so what have we covered in the beginning? So we discussed the difference between the symbolic computation and the numerical computation. As far as the integers and the rationals are concerned, there's actually not that much difference. But with the reals, we are in symbolic computation trying to avoid making numerical approximations. And if we make numerical approximations, we actually like to work with rationals so that the arithmetic does not incur errors. Okay, so internally everything is stored in a binary. No problem for the integers here. But with the real numbers, there are some interesting, how would I say, some unexpected consequences. So if we look to 0.1, then in the decimal representation, we would immediately say that this agrees with 1 over 10. However, as we will see, 0.1 has no exact binary representation, which in some sense means that when you work with numerical representations, so the approximations with the floating point numbers up to a certain precision, you will have a representation error. We have seen rational approximations with a prescribed precision. So we take any symbol, so like the square root of 2, we take an approximation, a floating point approximation with a certain precision, and then convert that result to a rational number. So then we are sure that the rational number approximates the symbol, square root of 2, with the prescribed precision. The second way how we approximated rational numbers was via the convergence of a the convergence of a continued fraction. So the continued fraction goes on forever with irrational numbers. We have seen that using the convergence, we can also build more natural sequences of rational approximations that are increasingly more accurate. So in this lecture we will see a third type of rational approximation where we can bound the size of the denominator. So that gives us another way to approximate rational real numbers, such as the square root of 2 and also the transcendental constant pi, with a rational approximation, but where you don't control the precision. You do not really work with continued fractions, but you work with the size of the numbers, which is relevant if you want somehow to bound the costs of your operations. So that will be the first part of the lecture. In the second part, we look into an application of sharing. So in the last lecture, I discussed how to make links between variables so the same object can be accessed by multiple variables. So then we considered a variable that was the name for a, a number essentially. So we can also use, of course, names for composite data structures. So in Python, a data structure that is extremely useful is the lists. So here you see an example, a list that stores three numbers. When you make that list, you not only make the name L, but you also make a list of other names, L0, L1, L2. So that's actually the first point of this slide here. The other point I want to make is that with a composite data structure, we have already the extra indirection. So what we had in the previous lecture was that a name X referred to Y and then Y referred to the object which represented the number 3. Here we have this indirection that is automatically implied by using the list. What this actually means is that if we have a simple assignment, so if we have another letter K and we assign L to K, then we actually are not copying the content of the list, but we are simply having another name for the same list. So lists are very useful also to share data. So that's actually another technique, another very common technique that one uses to sharing data, shared among different variables names. How can we apply this? Well, we can apply this to store data. We can make functions that remember certain things. So we will apply this later in the course to memoize recursive functions, to make recursive functions more efficient. This is kind of a preview of this. So this is not a programming class, but it's interesting that you know something about functions and functions that where you pass here an item to the function, and then when you call the function, typically you never access the data. So the second parameter is assigned to an empty list. So that means that when you call it for the first time, then memory is allocated for a list, and that memory, so the identification, so the address of the memory is actually stored in that data argument. So you see what the function does. It appends every item to the data. So the data is what is stored in this function. What happens the second time and every other next time this function is called, the list is already existing, so the same address is used, the same list in memory is used as the one that was used for the first time. So, and then the value of the new item in the next call is actually appended to that list. So, why you want to do this? Well, we will see an application of this. So this is the technique to do this. The picture that comes with this corresponds to this extra referencing. So if you have this list which encapsulates a data structure, but actually what you have is the reference or only the name. So symbolically, we typically do not think about addresses, not as programmers do at a lower level, but here we work with the names. So the name data, in some sense, is persistent throughout the uh, persistent even after the function is done running, which is rather unexpected because the formal arguments of a function one would consider as transient. So the item, for example, if it's a number, the item loses. So the item, the second time, the value of the item is simply overridden. But since data is a composite data structure, this does not happen here. Okay, so these are the concepts. Rather vague at this point, I admit, but I hope that it will become clear as we look at the Jupyter notebook. So I have a Jupyter notebook prepared, so if I ever blank out on something, I will go back to this. So the slides, let's put them aside for a while. So let me move the slides away and let me go to the demonstration part using Sage. Okay, so let me start with a new notebook. So in this seventh lecture, we illustrate number types and functions storing data. So these are the two main topics. So let me start with the number types, and I should have renamed this. So this is MCS 320, the worksheet that I'm using for the pre-recording. So what does Sage provide for us? So we have the letters ZZ, QQ, RR, and CC predefined. So for respectively the set of integers, the rationals, the reals, and the complex numbers. We haven't really actually looked at ZZ that much. So here you see it is just the integer ring. So at this point it doesn't seem to be that interesting, but ZZ is actually interesting for the conversion. So we can convert integer numbers to another base. So for example, this is the year 2022. If I want to see the binary expansion, so if I want to see the binary expansion of this, then I have to convert this number into the base 2. And how do I do that again? I have to ask for the digits, and the base has to be equal to 2. Here we are. So by the way, the most trivial thing was base equals 10. And well, it's not entirely trivial. So you see that the digits appear from right to left. So let me document this. Otherwise, this might not be clear. Observe that to rewrite the digits in the decimal expansion of a number, we apply the method digits for a given base as argument. Observe that digits appear in reverse order. The least significant digit appears first. So I can ask the bits of this number So this gives me the binary expansion of our year. That's kind of hard to see. I can reconstruct this also with the bits, and I have to tell that I want to see this in base 10. Okay, so the base is actually 2. I'm sorry, I want to see the value. There we go. Let me document that again. So we can evaluate the digits in a given base. Also, again, using the constructor ZZ of the integer ring. So we can convert from one basis to another. So we can ask for a number to see it in basis 3 and then convert it to basis 7, for example. The bases that are most interesting are base 2, base 10, and base 16. So let me, or actually also 8. So you can go to the octal. So other interesting bases are the octal and the hexadecimal number systems. So I can look at the number with, so I want to see the digits with base 8, and I can ask for the digits in base 16. So 16 has the advantage that if you are using the letters A, B, C, D, E, and F for 10, 11, 12, 13, 14, and 15, then the number can be written much shorter than in binary. So you could also see that the octal and is a regrouping of the bits with groups of 3. With the hexadecimal, you regroup in groups of size 4. Okay, so now about the reals. So let's take a random element. So let me look at the hexadecimal expansion. So for real numbers, we can look at the hexadecimal representation. So for example, I can look at the number, the year again. So let me look at the year, but now as a floating point number. And I can ask for the hexadecimal expansion. And you see that the hexadecimal expansion looks rather strange. So I do have a 7, an E, and a 6 sitting in there. While here you see the 6 coming in, so that's the least significant one. The 14, remember A is 10, B is 11, C is 12, D is 13, so E is 14. And then 7 is the most significant digit. And then we have the power. So the 0x means that the number is written in hexadecimal. So I have the 7e6, but then there is the power that is also indicated. And that is written then in also the notation for the shift, how you should see this dot here. Alright, so this is an exact representation. So we could see this also a little bit. So you need a finite number of bits to represent so with these number of bits you can exactly represent the number. This is not the case for, say, the 1/10. So let us look at the 1/10 case, or at the 0.1 number, which has an exact or a very short exact decimal representation, which agrees with the rational number 1/10. Okay, so let's look at 1/10. I will assign it. 1/10 is 0.1, and I will look at the hexadecimal representation. You see that the hexadecimal representation is 1.99999 and then some power. If we are extending the precision, so let us double the precision. So by the way, I'm using the default precision, which can be queried. So I have 53. So suppose that I want now 106. So I'm creating then a real field with precision 106. And what I'm doing is that I'm taking the 1/10 real field. I'm taking the 1/10, I'm casting it into that field, and I'm asking for the hexadecimal representation. And you see that I get a longer number, but it's still not finite. So I hope what this explanation here shows, so this demonstrates that the 0.1 has no finite hexadecimal representation. and therefore also not a finite or an exact binary representation. Which is kind of odd. As soon as we start working with 0.1, with floating point arithmetic, we start to make errors. Okay, so between the integers and the reals are the rational numbers. So we can make rational numbers from real ones. We can approximate real numbers by rational ones. So let me take a random real number, so a random element. So that's always very good if you actually have no idea what to work with. So we take some random number. So if you experiment with this, this will be a different number. Always interesting. But the properties that what I'm trying to illustrate now should be the same. So I can ask for a nearby a rational number where I bound the size of the denominator. So let's say that I want a rational number, but the denominator should be less than 1000. So here it is. So with nearby rational, with this method, we compute rational approximations of bounded size. So we like rational numbers, but they shouldn't be too large. So here we can look at the sequence. So let us make a sequence of consecutive rational approximations where the denominator is bounded by 10 to the power k for the kth element, starting with k at 1 and going up to 10 included. Okay, so I'm taking my x, my random number, and I'm going to apply the nearby rational with the max denominator now having a parameter in there, 10 to the power k. Okay, so but the k will range, so now I have to define what is k for k in the range 1 to 11. So why 11? The range stops at 1 minus the second argument. So here you see my list of rational approximations. Here we go. So this is a list where the size of the number, the size of the approximation is controlled. Let us verify the accuracy. So I will make another list comprehension. If you try to do this, perhaps do this first on one element. So what is it again, what I'm trying to compute? So the error is the element in the list. So I will have the element in the list So let's call it item, divided by, it's the relative error, the absolute value. So that gives me for item in the list. So that will give me the relative error. But I want to see the error in scientific notation. So I'm doing too many things at once now. If you try this, please break this up in pieces. I'm feeling rather confident right now. And you see that this accuracy actually grows very, very fast. Here it seems like I'm having 0 for errors, but this is 0, the 0 here drops below the machine precision. So that's why these last 3 rational numbers are indistinguishable from the x in the precision of 53 bits. So we've seen actually with the continued fractions that the error grows a lot slower. Here the error grows here with the bound on the denominator, so the number of decimal places in the denominator. You can also have a slower growing list if you let the denominator grow slower as well. Okay, that is the first part. Let me save this. I experimented a little bit. So here is another issue that I would recommend, that you often restart and clear the output and then you run everything again. So this has the advantage that you can kind of count the number of statements that have been executed. And if everything is free of errors, then everything runs as it should. Okay, so our second topic for today are functions. So here I have the slide still here. So I want to define a function that stores data. So let me use this. So here I will, in this notebook, I will make another section, functions to store data. And since this part is essentially unrelated to what I cleared the kernel already, but I want actually to reset everything. So we do the reset to wipe out, to start fresh. So we executed the reset to start fresh without predefined symbols. Okay, so let me then look back to the function here. So the function that I'm defining is the same as on the slide. So this is, by the way, how one defines functions in Python. So one starts with the prototype. What I did not do on the slide for space is a documentation string. And a documentation string is, in my opinion, mandatory, should be mandatory. So the documentation string allows to define what the function does. The function appends the item to the data and prints the data, prints the data and it returns the ID of the data. So data append item, print data, and then return ID of data. I will explain what is the ID of data. So this is our function, our Python function. So let me make sure that this is clear here. Okay, so here is where we are now. So we have our Python function typed in. The execution of the cell will provide us with some feedback if there are type errors, if we made some syntax errors. It will not execute the function. So with here you see everything went well, and I can start executing this function. So I will apply this function to the item 3. So here you see that I have the list printed out, and I also have the ID of the data. Let me append the next number and the next number. And you see that the function does what the documentation string was saying that it did. It appends, it prints, and it returns the ID. Okay, kind of magic. Let me now explain what happened. So the first time that we called the function, a new list was made, and that internally that list was stored in memory, and it got a location. So the big number here defines the location of the data in memory. So that's the I will try to explain what this ID is. So the ID data corresponds to the location of the memory occupied by the list referred to in by data in the default argument of the function. So I pointed this out in the slides, but here it was good pointing out again the fact that I'm always calling this function without these last arguments, without a second argument. I don't need to do this because it's a default argument. So the ID stands for identification number. So there is a unique identification number that is generated when the list is made, the first time we call it. That ID remains the same, so the second time that this function is called, we have already the identification of the list, and that gets used again. So that's why we see that there is the append. In contrast, the first argument item, that actually is lost. So the connection between, so we have two variables, sorry, not variables, we have two formal parameters, item and data. So since that each time I'm calling the function with another item, the link, the reference between the name item and the specific value is lost. In contrast, the second argument, data never changes. So that remains connected to that list that was created the first time. Okay, perhaps I should again flip to the slides and point at the previous slide. For here you see the reference to the list. So you see that when we create a list, then we can change the list. We can change also the numbers in the list by assigning to any of these names here. But what remains fixed is the name L. Similar thing is happening here in this function. Okay, so I'm nearing the end of this recording. So there's one last thing that I want to show, and that gets very technical. So how can you actually get access to this? Well, we can import C types. We can get access to the list maintained or inside the function. So C types refers to C, and the implementation that we use for Python is based on C. So how do I do this? I can get to the, if I have the ID number, so I have to do one more thing before I can do this. So I have to call the function one more time, and I have to get the ID of the data. So that's what I need. So it's not a good idea to essentially copy that number, because each time when you run the program, it will come up most likely with a different number, or on a different computer, most likely. So I have imported the C types. So and now I can use the ID of data, and it is so technical that I have to consult. I have to cheat a little bit. So this is just extra. So here are the statements. So I will copy and paste. So I have to import C types. Then I'm casting that identification to a C types, an object, and I'm asking the value. So this is rather technical, but just to make the point that if you have the name, you can go to the object, but you can also go in the opposite direction. If you have the location, you can go to the content as well. It's actually not quite the opposite, so you can follow the reference, but you can also, if you have the something to locate the memory, then you can actually get the value as well. It's very similar to what C programmers and C++ programmers do with dereferencing. When you have an address of a memory location, you can ask the value. So in this course we will actually never do this. So that's why these last instructions, I never really remember them. I never use them myself. But so that's something that is not so essential, but you should understand the construction that we have used here, because it will be become important later on the course. Okay, I hope this pre-recording is interesting, and I thank you for watching.